Hello and welcome to my presentation, actually the last one before lunch, so you already made it. I'm going to talk about learning a topological representation for stereo vision using a self-organizing map. First, I'm going to state it's still work in progress, so I have some evaluation, kind of proof of concept, but I'm not completely done here. Okay, first of all, the visual sense, just like cameras, maps the 3D world on a 2D representation, and we lose depth. Now, to recover this, in computer vision, usually when we have two images, we take a point from the one image and look for the corresponding one in the second image. We can then calculate the disparity. This is computationally quite expensive because of the finding the matching dot in the second image part. Yeah, so you can see here we have four objects, and they are like recorded from those two cameras, and we have 16 possible matches. And without any further constraints or anything, it's like impossible or very hard to distinguish which are the real objects, or which dots belong to each other in a way. So yeah, computer vision is struggling with that, so how are humans doing it? First of all, human depth perception uses a lot of different cues. Some is like a priori knowledge, is like even if we don't perceive any depth perception at the moment, we maybe did a second ago and our brain still uses it. And like oculomotor cues are maybe like how the eye muscles, when they focus on an object that's really close, they are like tense, and if the object is further away, it's like not that tense, and so the brain knows, okay, the object is further away. And we also have monocular vision. It's basically everything we can, every information about depth we can get from only one eye. It's a lot about prior knowledge, like we know how big some objects are. For example, bottle. If a bottle is far away, I know, if a bottle is really small, I know it's far away, and yeah. And last one is binocular vision, and it's basically everything we perceive with two eyes. Every depth cue we can construct by two eyes. We use all of them in combination, but well, some of these techniques are by themselves isolated quite inaccurate, and some even only provide relative positions, and binocular vision provides absolute values and is quite accurate, and therefore the most powerful. That's also why researchers this far have focused on binocular vision when they try to model human depth perception. Now we want human-inspired stereo vision. So a smart idea would be also to use human-inspired vision, not only for the stereo part, but for all. Because cameras are really different to how the brain and the eyes work. They transmit pictures synchronously, and which leads to a lot of redundancy. We don't do that. And one example of event-based sensors would be the DVS, which like all its components is modeled after retinal cells. Like the photoreceptor part by the cone, and yeah, you can see. Its course of action is basically if nothing happens on the image, it doesn't send any data. And if one pixel, the illumination changes, it sends an event. An event is basically just like the information where, when, and did it get brighter or darker. And well, this has some advantages. We have no frame, we have low latency, few computing power, which is really good because the correspondence problem already is computationally expensive. And yeah, here are some examples of DVS and newer and more sophisticated parts, like the ATIS and the Davis. Okay, now to our approach. The stereo correspondence problem can be seen as a dimensionality reduction. We have a stereo setup which like maps 2 times 2D data onto a 4D representation. Like here's the object in 3D, 2D, 2D, and we want a 3D in the end. Yeah. An efficient way to reduce high-dimensional data is given by self-organizing maps. They have been introduced by Kohonen. They have quite a biological background because of their topological structure, which is nice because, yeah, we're doing biological-inspired vision here. And, well, they basically, they are an unsupervised way to quantize high-dimensional data in a latent space of a lower dimension. And what's really important for us, they preserve topological properties. So neighbors in the input data, they adjacent neurons in the output. Yeah, learning is done by the best matching unit. We have a training vector, and, well, the best weight vector gets strengthened. For my evaluation, I have done some experiments with geometric shape. I used a cube and I sampled it. Here in the first row, you can see from the left and here the right camera, that's only, I think, the first 1,000 samples, and I used 100,000. And in the second row, you can see like the ground truth, that's the ideal colored, color-coded weights, and in the third row, that's what the sum does of the learning when we have random initialization. And I used the last row to emphasize that the shape is already quite like a cube. You can't really see it that well here. Yeah. Now about, yeah. This is basically, I tried a simple and fast way of 3D reconstruction, and what's important for me, it's quite memory friendly. Well, that depends a bit on what cameras I use, how many pixels, and yeah, but in general. And yeah, I started with the implementation and evaluation with event-based data. Here you see a pendulum. That's like the samples of the first stage we saw previously, like here. And yeah, I haven't included it as much because I'm not quite finished and it isn't really part of the abstract as far. And yeah, that's my team. I'm also in the lab of Camillo, who was already mentioned.